So, welcome everyone. I'm happy to give the first talk today. The group I'm representing is the group connected with topic 1, theory of gravity, mathematical structure, and applications. The main topics of our group, let me first begin by saying a few words about our group, is theory of gravity, the mathematical structure, astrophysical and cosmological applications, which is both applied GR applied to cosmology, light propagation, homogeneities, and mathematical relativity. As for people, so basically we have two professors, Professor Kijowski and myself. Apart from that, group consisted of 4 people, two of which have completed their stay at CFT last year. So Nezihe Uzun finished her Polonez bis in November 2024, and Mateusz Kulejewski defended his master thesis under my co-supervision at Warsaw University. Professor Kijowski has 2 PhD students as well. Regarding our collaborations, I have a collaboration with Asta Heinesen from Niels Bohr Institute. We are working on the redshift and position drifts in cosmography, so slow variations of position and redshifts of distant objects in the universe and what you can learn from that. I also mentioned Mateusz Kulejewski. He wrote his thesis about the effects of transverse motion in axially symmetric gravitational lenses. I think he will give a talk about that at some point at our institute. Professor Kijowski is pursuing his 3 projects I've mentioned here. And also he has a collaboration with Gerd Rudolph at the University of Leipzig. This is the master thesis of Mateusz Kulejewski about the effects of motion in gravitational lenses, defended last year. On top of that, Professor Kijowski gave a lecture on quantization at Warsaw University, and I gave a lecture in 2024, an introductory lecture to general relativity in the Geoplanet and Warsaw for PhD schools, and a bit of advertising. The lecture is available at on the YouTube channel of CFT. I think it went fairly well. Here are the papers. So here I'm showing 4 papers and 1 still preprint. It's 3 papers by Professor Kijowski's group, 2 papers from the side of my group. I will talk about this one. So it's written together with Nezihe Uzun about algebraic symmetries of the observables on the sky, variables, emitters, and observers. I don't have that much time, so I will just give you the flavor and basic idea of what we are working on. So both me and Nezihe Uzun worked on what I would call the bilocal approach to geometrical optics in relativity, which is a kind of unified view of many types of observables, which happens when you simply have a source and an observer and a connecting null geodesic, or more precisely, a family of null geodesics, representing an image on the sky. It turns out that this situation has this very interesting algebraic structure related to this situation, and this results in certain exact relations between observables which all can register. Let me tell you this more in detail. So imagine that at some point, some light emitted at E basically is later received by an observer at the point O. From that we can define the 3 primary observables: the position on the sky defined by the wave vector of this wave, the redshift defined by the frequency ratio, and the viewing direction, which is the direction from which we see this body over here. But I'm more interested in variational observables, so observables which tell us how these things change when we displace the observer a little bit or we wait for a little bit and see what happens in time. These are the drifts, but also the magnification, the angular size, the trigonometric parallax effects, the angular diameter distance, and there is many, many more. All of them are related somehow to the variations of these things when you displace one of these points over here. In each of these observables can be expressed as a function of both for velocities of the source and observer, their accelerations as well, and a special object which encodes basically the way the space-time, the way light travels through the space-time. This object I call W is basically a huge matrix, and it's a function of the curvature along the line of sight. But it's also known that this object has certain known algebraic properties. And these properties imply certain relations between various observables we can define here. What could be the observable consequences of that? There is one consequence which has already been known for years, decades in fact, a relation between the luminosity distance, or distance defined by the flux of energy from this body, and the angular diameter distance, distance defined by the apparent size of an object whose transverse size we know. It turns out that they're related to the redshift or the frequency shift as well. And this is supposed to hold in any space-time whatsoever. There's no restrictions. It's a general identity regarding geometrical optics. And what we want to do is to produce more identities of this kind and see if any of them are interesting. Where does W come from? Basically, W is the resolvent of the geodesic deviation equation along a null geodesic. So we can write the geodesic deviation equation governing nearby geodesics as a first-order system for 8 components. It has a resolvent. This resolvent can be written as satisfies its own ODE, which is in which the curvature plays an important role. It's a mapping from the observation point to the emission point. It has obvious resolvent properties. It has certain algebraic properties with respect to the tangent vector to our null geodesic. It has to preserve it in a certain way. But the most important part is that it preserves the symplectic structure. There is a symplectic matrix on the space. W is acting, basically the cotangent space to the manifold. And this is always preserved. Let me. In order to derive all the consequences of this property, of this symplectic property, we move to a different type of representation. Here, the geodesic deviation equation tells us what happens when we displace the initial point of the geodesics and displace somehow the direction of propagation. But we would like to swap this picture to the boundary value problem. What happens when we displace the observation point and the emission point? How do the tangent vectors change in that case? That's passing from W to U representation. And it turns out that this is algebraically not that difficult. What is less trivial to see is that this is in fact the same type of, it is exactly the same type of relation in both directions. So you do the same matrix transformation from W to U, and if you reapply it, you are back to the W representation. And what is the most important thing is that if this W matrix originally is symplectic, then this matrix U has to be symmetric and vice versa. So the condition that this is symplectic is basically equivalent to this being symmetric. And this is much easier to use. We can then define various types of observables, for example, those related to the drifts or the temporal variations. You have to make sure that both endpoints are connected by null geodesics. This imposes additional constraints on the way we displace both endpoints, the emission point and the observation point. If you play a little bit with the algebra, you can get, for example, an equation for the variation of the redshift as the observer registers when observing the source. And this is a completely general equation in any spacetime whatsoever. You can also describe the magnification matrix using U, the parallax matrix, and other things. I won't bore you with that. And then you can try to see what are the consequences of this thing being symmetric. So some of them were known. The Attendon relation basically is related to this, to the so-called Jacobi matrix to be equal to the reverse Jacobi matrix transpose. But on top of that, we have also the fact that the parallax matrix, so the matrix which gives you the apparent displacement of a body when you move sideways, it has to be symmetric no matter what. But the one we found most interesting is the one we see here. Basically it tells you that what we call the parallax of the redshift is related to the position drift. Here's an illustration of the situation. So we have a source, which is moving in any spacetime whatsoever. We've got an observer, and we measure the frequency of the wave coming from this observer and the redshift from that. But we assume that we also have two other observers who are displaced in transverse directions by a small amount. They measure slightly different frequencies, and I call this effect the parallax of the redshift. It turns out that this effect is precisely equal to the apparent velocity of this of the image of this object on the celestial sphere minus the simple effect of stellar aberration. This is a fairly trivial consequence in special relativity. You can derive this equation quite easily. But the bottom line is that it works exactly the same way in any curved spacetime whatsoever. Apart from that, there are also certain relations pertaining the viewing angle or the variations of the angle from which we're observing a body. And this is much less of an observable in astronomy than you might think, so we didn't find them very interesting. This one we found quite interesting. This one was already known. This one, I think there was at least one author in a very different paper who also knew that this matrix has to be symmetric. But in any case, we managed to basically exhaust the topic, and all possible consequences of W being symplectic are listed over here. Thank you very much.
Are there any questions?
Because, Mikołaj, it seems that you saturated the topic, and what are your future plans?
Different from that. So I want to abandon the theoretical work on this thing because I don't think there's much to write about it. I want to work, I'm mainly working on two topics. One of them is the observational application of that, or more precisely, what you can learn from the redshift and position drifts of distant objects. That's a collaboration with Asta Heinesen, including some work with the data from Gaia and a satellite. And on top of that, I want to publish my, I think, quite interesting results regarding the lensing by moving lenses. There is very interesting results there as well. Yes? Wait.
Thanks. So actually I had a sort of a technical question. So this was probably this Polonaise Bis project of your collaborator, yeah? So how did that project go actually? Was this her idea and stuff like that, or?
It depends. So basically she worked on her own project on including, so her old project was more about Neziha's project was more about including the wave effects and wavization of geometrical optics in GR. And this thing over here, it was more my idea, but she also wrote a paper about this W matrix being symplectic, but as most people, she was only interested in, let's say, a subspace of the full space of solutions. So since we were both working on the same topic, it felt like a good idea to me to work on that.
Any other question?
I have a bit maybe silly question. So you incorporated, let's say, effects or consequences of this geometry for like geometrical optics. Okay, so what about quantum effects when light propagates? Like, do you foresee that maybe when light is somehow entangled, you'll get some interesting effects from in this setup?
So this is very far from any kind of quantum effects. This is at the level of geometrical optics where you're allowed to talk about light rays, the precisely defined direction of propagation of a wave. There is many steps from quantum theory. And to be honest, I don't know how to bridge this gap, and I'm not even sure it's worth doing that.
So I propose that we move to the next talk. Let's thank Mikołaj again for his nice presentation. So our next speaker is Wojciech Bruzda, who is actually my postdoc, but he will replace Professor Kuś in presenting the achievements within the topic number 2. Please, the floor is yours.
Thank you very much. This is a pleasure for me to be here, and I will present the group of Marek Kuś. The statutory task is composite quantum systems and their applications. These are the leaders of the group, Marek Kuś and Karol Rzeczkowski, and they are occasionally supported by other people from CFT. A comprehensive list of the names is put here. These are selected papers, only selected papers. A full list can be found elsewhere. As you can see, each member of the group presented and published something last year. Okay. Now let me skip to the most interesting part of my presentation. The title is Quantum Circuits for High-Dimensional, Absolutely Maximally Entangled States. This will be a short story about quantum computers, not how to build them, but how to certify them. Let me briefly set the scene and introduce the most important concepts I will use for my presentation. Quantum entanglement, many-body quantum entanglement. As everybody knows, the quantum entanglement forms are kind of very strong correlations between two or more physical systems. And we can measure entanglement. Measure indirectly, because in quantum mechanics there is no entanglement operator. We cannot just look at the eigenvalues and say what entanglement is, but we have different methods, indirect methods, to quantify and qualify entanglement. It could be no entanglement, it could be some partial entanglement, and what we are interested in is maximal entanglement. Not only maximal entanglement, but absolute maximal entanglement. So our scenario is the following. We consider pure states in a Hilbert space which splits onto 4 components, and each component has local dimension d. In particular, we are interested in this particular dimension, d equals 6. Why? Because for many years it was an open problem whether such absolutely maximally entangled states exist in such regime of such multipartite scenario. There is also some short story about graph state formalism, but I'm not going to explain this right now, probably. Okay, so this was the question we posed several years ago, and then we answered the question. We proved that such states exist. In particular, this is one possible representation of such a state in a form of 36 by 36 unitary matrix with a very particular internal structure. As you can see, this matrix is very sparse. These colored dots, let's say, represent, their different colors represent different amplitudes of non-zero complex values. And, well, okay, that's it, okay? Once we have it, last year I showed you this diagram because we immediately asked, how can we realize such a state in a real laboratory? In other words, can we express a particular representation of M4-6 state, 4 parties, each of local dimension 6, as a quantum circuit? And our motivation was very natural because, first of all, nowadays, everybody's into qubits, non-qubits. Let me show here. This is not equal to 2, so it doesn't represent multi-qubit state, but Q-hex state. So we are in the regime of qubits, actually, and now everybody wants to build or to propose quantum machine which operates on higher dimensional Hilbert spaces. Also, because this state is very quantum, it is absolutely maximally entangled state, it is very good thing to benchmark nowadays noisy quantum processors, quantum processor units. Also, it serves as a quantum error correcting codes. And of course, it improves many teleportation schemes. For instance, it performs better in comparison to GHZ states. Whatever. Okay, last year, our knowledge was very limited and we didn't know what to put in the place of this question mark. Exactly 1 year ago, March 22nd, 2024, the work was in progress. But times passed and a group of people joined together and we realized 2 things. First thing was we unexpectedly discovered that there are many other inequivalent solutions that represent this very particular state. And we were able to decompose this question mark onto this particular circuit. The construction is based on so-called B-unimodularity. If you have a vector of complex numbers, such that every entry in this vector has modulus 1, then we say that it is B unimodular if it remains unimodular after a Fourier transform. So if you can find such a vector, you can use it to a construction of this particular state and put it as a one component, one quantum gate in this big quantum circuit. So this is how it looks. So our Q-hex lines, because let me skip again here, these 4 lines, each line represents one particular subsystem. There are 4 of them, each of 6-dimensional. Can be split onto 3 qubits, or rather I should say not split, by embedded into 3 qubits. So these are standard qubits, 2-dimensional Hilbert spaces, 6 into 3 times 2. And our unitary matrix, which represents our state, can be decomposed on the elementary gates like this. This CZ is a control Z gate defined in here. Here are some Fourier transforms operating on single lines. And there is one bottleneck. One bottleneck is this huge diagonal matrix, huge diagonal 36 by 36 diagonal matrix, which consists of third-utes of unity. So if we are able to decompose this guy here, then we are done. And we are done. This is the solution. It's a bit complicated, but it works. One can check that it really works. Let me explain this very briefly. First of all, there are only 2 gates in this big picture. You can see there are only RZ rotations. RZ is just okay, never mind. This is just a kind of rotation, which is an elementary gate and CNOT gates. And okay, it starts here, it goes there, and again, it starts here. So this is a very, very long line of gates in this decomposition. And it allows us to try to implement it in a real laboratory to check how it works. We don't claim that this is the most optimal decomposition. Probably one can simplify this. Maybe just removing 1 gate or removing 20 gates, because it has like, the cardinality of the gates is like 100 something. I don't even know how many of them there is in here. But we don't know. So, okay, the work is done, but it's still ongoing because we're still looking for a better representation of this state. And we are looking at an experimentalist who would like to implement it in a real laboratory to check if our predictions are okay. If you wish to know more, I can explain it in the poster session. Thank you very much.
Okay, thank you, Wojtek. So.
Why 4 and 6?
Because the existence of such a state in this particular Hilbert space was an open question for like 20 years, and nobody knew at that time whether such states ever exist. So this is the first question, to prove existence of such a state or to rule out its existence. If it exists, and if it has all these properties, being the most quantum state, according to some definition, I didn't put the definition because it is not so relevant in here, then it might serve as a good benchmark for quantum machines. That's the short story about motivation. We solve the problem. We fill the gap, so to say.
This is an example, of course, because...
Yes, there are many other examples, but this was particularly interesting.
Yeah, thank you for a nice talk. So you said, I have 2 questions. So first you said that everybody is about like qubits, right? So can you like name like some platforms where you think it would be like feasible to implement what you propose? Second question is, do you have some circuit lower bounds for the depth or number of gates needed to prepare this kind of states? And how close is the construction that you propose compared to those bounds, if you have them? Lastly, you have this diagram, like, and the first part of the circuit is very special. Is it really fixed? or because you filled some box in it, but like why the beginning is like this?
Okay, I try to address these questions. Why by the other? We don't know. Okay, we don't know, and we know it's a partial knowledge because, as I said, this is our motivation. So, if anybody is able to implement such a state, because it's not so easy, because okay, everybody's into qubits, but nobody has a possibility to work on qubits actually, because this is very hard. Even qubits are very demanding to be done in a laboratory. But if anybody has some setup which is intended to work in a qubit regime, it would be very good benchmark to check whether its setup is really working or to what extent.
It's fine if you don't have like lower bounds. I understand the motivation. I comply with it.
Okay. What was another question?
Yeah, like one by one. Right. So one question was, let's say, about the circuit lower bound. So you have some construction of the circuit that realizes this AMA state, like it has some gate count, some circuit depth. Do you know, like some like lower bounds for the circuit depth needed to realize such a state? And if so, how close is your thing compared to those bounds?
This we don't know. That's why I don't know how optimal or how not optimal it is actually. Of course, we can extend it very easily, but to compress it is a whole other story. Right? We don't know how far can we go with optimization of this thing. And okay, I remember the third question. It was about this particular diagram, why it starts with this. Yes, is it correct? Because at the very beginning, okay, this is not so easy to explain. Probably I can elaborate on this during the poster session because we need this requires some background. Okay, why this always appears in such a decomposition.
Thanks.
Okay. Any other question? So maybe I will have one. So you presented on the. Can you go to the slide where you have all the lines? So those lines represent qubits, right?
Those lines represent qubits. As it's written here, each Q hex is mapped into 3 qubits. So these 6 lines, six lines in here correspond actually to these 2 lines. First Q hex line and second Q hex line. And these 2 are done because they do not somehow affect the whole thing.
So still you have too many lines, no?
Still, it's too many lines, but this is the first try.
Okay, so let's thank Wojtek again for the nice presentation.
Thank you very much.
And I invite Krzysztof Pawłowski to the stage. Krzysiek will present his group that last year was the richest group in the institute. Let's see what's the status now.
So this is the group. Actually, I should use this one. Actually, there is Michał Matuszewski, who was last year still in our statutory topic, but this year he will split. Actually, he will have his own topic. But still, last year he was in statutory topic 3, so quantum gases. And the leader of the group is Professor Rzążewski. He was implementing Opus project with 2 young people, 2 young researchers. One is actually from University of Warsaw and the second from Institute of Physics. My group was financed from Sonata BIS, but Bura just finished his postdoc in the middle of the last year. Kuba Kopeciński finished his PhD in September, and still Maciek is here. Maciek will defend this September, but there is no new person, Maciek Tusarczyk, student from Warsaw University of Technology. He will join our group and hopefully become a PhD student. Then Wiktor, he was directing Polonez BIS, which was also accomplished last year. And we have Lech, so chairman of scientific council, who published one paper last year. Or it was actually accepted last year and published this year. So these are the papers. I split it into 2 columns because, as I said, Michał will split to another his own statutory topic. And actually, Michał had the very nice publications, including this Nature Materials, which was discussed during our colloquium a few months ago. And Michał have also talked about quantum part of this, well, polariton business during BSc seminar soon. Concerning ultra-cold gases, well, this year was not so good, I would say. So we published 4 papers, 2 JFIS-B and 2 PRA. Actually, most of these papers were published at the beginning of last year, so they were published because of results from the previous year. Other achievements, so as I told you, Kuba Kopeciński finished a PhD under my supervision. Apparently it was not bad PhD, as he received FNP START scholarship for achievements from this PhD thesis. But now he moved to Paris. He's leaving science actually. And from achievements, I managed to get a new project, Opus, from NCN. Outreach activities. Some years ago, we built together with Jacek Szczepkowski from IFPAN the machine demonstrating quantum protocol, BB84, and we are still using that. And last year it was used in between during a science festival in Warsaw. So we have workshop, we have a lecture about that, and actually I think there were quite many people who wanted to play with this device. But 3 groups. And the big achievement is Iracher. So I was writing big parts of the project, but this is not not associated with our topic. It's a more institutional project. So now the scientific part. I wanted to make some distinctions. So in CFT, there are astrophysical and cosmology groups and quantum groups, and to give you a grasp what we are doing. So in cosmology and astrophysics, as we know from different colloquia, you are able to simulate many objects, 10,000s of objects, using classical equations of motions, including or not magnetic forces or electric forces. In our case, so my group is also doing something similar. So we are often writing codes or some models to describe real physical systems. The difference is that there are laboratories, so we can discuss with experimentalists and ask them to prepare something, or they are asking us to explain some effects. And the other big difference is that in quantum physics, well, here in this classical description, you can introduce, for instance, the probability distribution, which is practically single particle object, which is maybe complicated to solve, but it's single particle in the essence, describing all these many objects at the same time. In quantum physics, we have to deal with a wave function. If you have n particles, this wave function is a function which depends on n variables. So modulus square of that is the probability distribution, which is living in n-dimensional space, which is making these problems much more difficult to solve. And in particular, we are often limited by concerning the number of atoms by 10, for instance. So this is our maximum to do the simulation. And there is, we are very happy if there is a model, which is many-body model, quantum model, and which has exact solutions, analytical one. There is such a model which is relevant to our discipline, which is Liebling model. This is describing n particles just in the box in 1D, box with periodic boundary conditions. These particles can move. So there's this kinetic energy operators for every particle, and they interact with themselves via delta function. So this model is called Liebling model. It was solved in 1963, but still there are many researchers working on that, and there are also experimental group implementing this model or its extensions. So what this model is predicting, so already Lieb in 1963 found ground state energy almost analytically. So he replaced the original model with a simpler one. So here is the energy of the ground state as a function of, let's think, G, so the strength of the interaction. The energy is zero if there's no interaction between atoms. And then if interaction is stronger and stronger, it saturates. So this is a funny thing that even if the interaction strength is going to infinity, the interaction energy is saturated because the atoms are arranged in such a way that they never meet, such that the interaction energy is actually going to zero. And there is a funny thing about that, about states which are achieved for very strong interactions, because they are very similar to fermions. If you take many-body fermionic wave function, so wave function which is antisymmetric, and modulus of that, then you will receive many-body wave function for bosons, which turns out to be actually this ground state which is here. That's why this region is called fermionization, because you can easily map this regime to non-interacting fermions. And there's also other funny thing that if you look not at very strongly repulsive atoms, but very strongly attractive ones on this side, then there are states, very excited states that are similar to the ground state for a repulsive system. They're not exactly the same, but very similar. This region is called super-Tonks-Girardot regime. So these states here are very excited. So the ground state is a state where all atoms try to be in the same spot because to minimize energy, if the interaction is attractive, we'd like to put all atoms in a single point. But there are some excited states which are very similar to these ones. That's why the group in Stanford managed in 2021 to do something which is called topological pumping. So they have a method to change the interaction strength, this G parameter. They start, let's say, from the almost ground state. Then they are reaching this fermionization region, and then they can switch the interaction strength from something very, well, plus infinity to minus infinity. Then they are jumping to the super-Tonks-Girardot regime, and they are increasing interaction strength, here's modulus, to reach some excited state for the ideal gas, and then some excited state in the fermionization regime. And they were interested in states which are obtained in this Tonks-Girardot regime, in this fermionization regime. And we looked actually at states which are obtained for the ideal gas during last year. So somehow no one was interested before in these states, but we thought that these states could be important because if you have a state where there is no interaction, then you can maintain the state for a longer time and avoid different dephasing and different decoherence effects. So Maciej was looking at these states together with Bruno Julia Diaz from Barcelona and Grigoria Strikarczyk, also from Barcelona, when he was investigating the whole topological pumping. But these states for ideal gas turned out to be very interesting. So it turned out that if you look at the momentum distribution of the gas in these states, then this momentum distribution looks like that. Just a single peak at different and equally spaced momenta. What means that momentum distribution of these bosons are exactly the same as momentum distribution for non-interacting fermions. Of course, the states are different, but the momentum distribution looks the same. And if you look at the higher and higher states, then the structure is maintained by the distance between these peaks is larger and larger. Having this one can easily compute first-order correlation functions and other functions. One can, having this and knowing 1D physics, one can find the equation of states and something which is called Tan's contact for these states for ideal gas and strongly interacting system as well. So this was the project which Maciej was implementing. I found it relatively easy to present. That's why I decided for this one. But actually during last year we were also working on a few papers That's why I think that this year we have many publications. But last year was not so good in this respect. So thank you for your attention.
Thank you, Krzysiek. Are there any questions? Well, it's a nice occasion to ask Krzysiek questions about his research.
So, of course, one wonders how fragile is this ideal gas state? Because it certainly has a very interesting momentum distribution.
Mm-hmm.
And as you mentioned, one might think that it doesn't dephase as much, but is anything known about this state here? I mean, okay, I guess they managed to get it experimentally to some degree.
Yes, although they were not interested in that somehow, or they missed that there can be something interesting. That's why they didn't analyze these states. But as they were able to do this topological pumping for 30 atoms, it means that the states, well, it was proved experimentally that it's somehow stable. How stable it is, we don't know, but one can slowly pass this state and nothing is happening.
Okay, let's thank Krzysiek again. And the next speaker is Agnieszka Janiuk, who will tell us about the astrophysics group.
Okay, hello everyone. So I represent astrophysics group, which consists of two subgroups, me and Professor Czerny. And unfortunately, I don't have a slide with photos of the group members, but on the other hand, we are all today in person here, so you can meet all of us and our students and postdocs who are currently at CFT in the poster session, because everybody prepared also a poster. This is the first half of our publication list, the ones which I am co-authoring. And this year, there were several nice works published. Two of them appeared in Nature, two of them in Astrophysical Journal Letters, and also in APJ. These two works were published together with the former members of my group, Fateme Nouri, currently working in the Italian Institute in Milano, and James Pestin, who got a postdoc in Paris. And these works were published 2024, but prepared 23. So we are interested mostly in the transient and multi-messenger astrophysical phenomena. This is one of the two legs of my group. These transients are the cosmic sources, which typically involve compact objects, either coalescence or collapse of a star to form a black hole or neutron star. And in these systems, the gas propagates with relativistic velocities. And they are transient because we have only very short time to observe the main characteristic of the cosmic phenomenon, and that's how we are motivating our models and trying to explain observations, but they are quite difficult to study. There is also another leg of our group, the time variability of accretion. These sources are not so transient, so we can observe them over longer timescales, and also they are typically involving compact objects, black holes, neutron stars, but the gas here does not move with so fast speeds, mostly with subsonic velocities in the accretion disk that evolves over times of months and years, and we can have long timescale of the observation, and multi-wavelength observations are also available. Main topic of the grant from the National Science Center, the Opus grant that is finishing now, was the gamma ray bursts. And the gamma ray bursts were studied together with my postdoc Gerardo Urrutia, and also a PhD student Joseph Saji. They both prepared posters today, so I will not talk much about gamma ray bursts by themselves, just to show you the idea. This is the source of the relativistic jet that is powered by accretion onto a newly formed black hole. And these events are these transients which we observe in the sky. But our methodology is theoretical and numerical studies, and they are based on general relativity and magnetohydrodynamics. Sometimes we can simplify our problem and skip the GR or magnetic field, but in gamma ray burst case, of course, we cannot. And we have to describe the motion of magnetized gas in a gravitational field. We are solving the system of equations. These are the continuity equation, mass and energy momentum conservation equation, and the Maxwell equations. These equations are solved numerically, so we have to discretize them on the grid, and typically using finite volume methods when the quantities are represented as volume integrals in the cells of the numerical grid. And our scheme advances the time evolution of these conserved variables. Also, using inversion scheme is essential to recover primitive variables from the conserved ones, because in GR we have two types of variables like that. I will skip the technical details, just refer you to our website. Here is the address of our website, and you can find more details there. I just want to thank not only the National Science Center, who is supporting our human resources, but also to the supercomputing centers, PLGrid, who is supporting our computational resources. We have to apply for external grants to use supercomputers through the Polish and international centers. I would like to highlight today two main results which were obtained last year and published last year. So first of them is modeling of the active galaxy center through the MHD simulations. This active galaxy here is the famous one, M87. This is the image of this galaxy taken by the Event Horizon Telescope. We know already for many years that this is also the galaxy which is ejecting the relativistic jet that is powered by accretion onto this central supermassive black hole. But in this work, we did not study the jet actually. We studied the broadband data and fitted them with a model that is shown here. Several components of this model represent the synchrotron and Compton emission, and the data were nicely fitted, assuming also some kind of hybrid electron distribution. Anyway, this is quite an achievement to fit so nicely the broadband data with a single model that is physically motivated. And this was done thanks to the collaboration with Andrzej Niedźwiecki and Michał Oszmaniec from the Łódź University. They have this code for computing GR radiation transfer models, and these ray tracing models are used here to produce the synchrotron emission spectra. And the second paper I want to advertise today is this Nature publication, together with, I think, about 50 co-authors here. Matt Nicol from the MIT and several people from there, and international team of researchers, mainly observers. They took multi-wavelength data from many high-energy missions. Chandra, NICER, SWIFT, XRT, and AstroSat are the X-ray telescopes. On satellites, also SWIKI provided the optical data for the newly discovered source, and this is actually a new class of sources. Some of them are shown here, I mean all of them, yeah, this is the sample of these sources. And the one here marked with the black dot is the subject of this paper, the AT 2019 source. And it is called a quasi-periodic eruption because the source exhibits luminous bursts of X-rays from the active galactic nucleus, and they are repeating over very short time scales of hours to weeks, depending on the source. Yeah, here is the plot showing the mean recurrence time of these outbursts, and here is the plot showing the mean recurrence time as the function of the black hole mass, and here as the function of the mean duration of the cycle. So anyway, this is the observation of the source AT 2019. These are the data points. It is interpreted as the accretion disk around a supermassive black hole undergoing some instabilities or interacting with a stellar object in a close orbit. That should also give similar type of behavior. About the accretion disk, we speculate that it could be created when the supermassive black hole is disrupting a passing star. This is called a tidal disruption event of a star. This star is destroyed, and we have a transient phenomenon of this accretion disk that is showing such instabilities. And we had a model about this. The author of this work is Marzena Śniegowska, former PhD student of Bożena Czerny, and we provide one of the possible explanations, the disk instability model and its hot corona, driven by the radiation pressure oscillations, is a possible QP mechanism for intermediate mass and supermassive accreting black holes. The code which I wrote is also available, and you can see another application of this code in the poster proposed by new PhD student here, Bilicki. Okay, to celebrate this achievement, we organized a conference together with Bożena in September. It was a 3-day conference co-financed by CFT generously and by NAVA. About 50 participants from Poland and from Italy, US, Israel, and other destinations. So this is our conference photo, and I would like to thank also our local organizing committee, Gerardo and Bożena, for organizing a nice dinner on the boat on Wisła River, and to Pani Magda for all the help, logistics of the organization of the event in the hotel of O3. Another achievement that I'm very proud of is this Impact Award on the joint undertaking Euro HPC event, where I got an award in the form of diploma, and yeah, congratulations from the director of the Euro HPC supercomputing centers, because I won 2 new computational grants on the LUMI supercomputer. That is one of the most powerful in the world now, the number 8 on the top 500 list of the supercomputers, and this award ceremony was organized for the users of various European supercomputing centers in Amsterdam, November last year. And finally, this is the second half of our publication list. All the papers co-authored by Bożena. So altogether, we have quite a number of achievements, but for those, you need to go to the poster session really and see how the guys are determining the Hubble constant there. Okay, this is my summary, so I will just flash it. Thank you.
Okay, thank you, Agnieszka. So it's clear that our astrophysics group is very active and productive. So are there any questions to Agnieszka? It's good to have you here.
Okay, but I always have sort of strange questions. So I noticed that you have, like, for computational hours, you had 15,000 on LUMI and 10 million in PL grid. So how many hours?
This 10 million is also on LUMI, but the application system is through the PL grid. You can choose LUMI from the PL grid application.
I see, it's like this. So I'm not sure if my question is sort of useful then, because I wanted to ask sort of how many hours of PL grid is equivalent to 1 hour on LUMI? Well,
I can estimate this, but basically LUMI is very powerful. So each core, each node has 128 cores. Yeah, if you have this number, and also it's much faster. So yeah, I mean 1 day of computation of LUMI is equivalent to a couple of weeks on RS in Kraków. Yeah.
I think that this computational power is absolutely impressive. Do you have an idea how we can describe it in terms of some currency like euro? How much is your success worth in money?
I don't know. I mean, yeah, to check that.
Somebody would like to buy this time.
1/10 of the time.
Well, that is actually a good question, because once I asked about this, but I asked this at the Warsaw University ICM, because I ran out of time on their computer, and I learned from the former director, who is not there anymore, about the possibility to buy some computation time from my NCN grant or whatever, private money. But yeah, the price was huge. It was huge because it was they have even some kind of a offer, yeah, formal list of prices per hour, and it was, yeah, huge. I mean, yeah, 50,000 zloty or something, yeah, like this. So this is commercial price then.
Okay, let's thank Agnieszka again for the very nice presentation. And the last speaker of this part of our session is Lech Mankiewicz, who will tell us how to teach physics at primary schools.
Okay, so I was listed previously in Krzysztof group, but probably that was correct, but I have been moved to the Science to Society again at the beginning of this year. Anyhow, I will report on that. I must apologize, I don't show anything about Łukasz. I decided not to bother him, basically, with collecting this information. But, well, the make long story short is that a few years ago I was recruited as a physics teacher in a grammar school. And I went there being absolutely sure that I am first-class expert about teaching. You know, Khan Academy is my child. Khan Academy in Polish is basically my child and my achievement of a lifetime. So I would tell them, I would show them how to teach. And that was actually incorrect assumption, because it turns out that the theory is one way and the reality is other way. So, oops, excuse me, okay. And so last year I gave a few talks, mostly explaining people at various conferences that what they think about teaching and all these modern ideas is actually not really very useful. After that, of course, I will not be invited any time more for this type of conference. Basically, what I discovered, and that's, I think, I want you to take away from that, is that actually the same internal force which drives us, an interest in inquiry and pride and satisfaction from solving problems, thinking about problems, even not solving, because that comes rarely, but first of all, there is a lot of thinking about problems. The same force can be awakened and drives students from 6th to 8th grade. Earlier, perhaps not so much, because there are some neurophysiological mechanisms. The axons are not ready to conduct electrical pulses in sufficient speed, so that kids start really to be able to think in abstract way, which is the key of understanding of anything, right? Basically, sometimes in the 6th grade, and some of them only in the 8th grade. So I teach physics in 7th and 8th grades, and I treat them with a lot of hands-on experiments, which I devise or borrow from various sources in the internet. A special project in the 6th grade, when I realized that they have enormous problems with abstract thinking. I tried to wake up this abstract thinking using simple problems in 6th grade already. and math clubs in 6th, 7th, and 8th grades, where I continue this education with some maybe more talented or maybe more interested students. Actually, many of them do not really realize that they can be interested in or they can feel well by thinking. This is not what is practiced nowadays, neither at home, not at school, at early stages, partially because they cannot think in an abstract way, and partially because we have learned to understand education as memorizing a set of recipes, basically, a set of steps. And I very much encourage you not to treat your students in this way. I understand that all of us has a problem to solve, and therefore the most useful student is just an interface between you and a machine for problem solving. I mean, takes a list of orders, recipes, and goes through it and then produces a result, but this is not the way people develop, really. People develop by thinking about problems and finding original solutions, notwithstanding how easy a problem is. The same works for 6th grade as it works, I understand, for PhD students. I must tell you that I was, for all my life, a person who was trained and proud because of ability of solving fast problems, not thinking enough about them. I am very happy with my career, but it could go different way if I spent more time thinking and less time trying to solve another problem just because I know how to do it. So that's in other direction, yes. So this is in modern lingo what I do, and especially I am very proud about the second bullet point because indeed emotions which can be raised by simple mathematical problem, both positive and negative emotions, when your students realize that the problem is so simple that they could understand it but they didn't manage. However, a colleague did. When I, at the very beginning, didn't measure or estimate those possible emotions in appropriate way, I had students crying by this exercising in thinking, just because they wanted so much and they were so disappointed that they failed, and a colleague did. And so then I learned somehow to present simpler problems. And that's, of course, extremely important because if we think about society which is capable of resolving problems in a reasonable way, people have to learn how to think, really. And this is very unpopular because, what shall I say, a lot of people coming from the corner of sociology or economy behave like they would never have solved any problem, really, and just don't feel those emotions, never felt those emotions. They just don't realize how powerful simple mathematics is in creating positive emotions and moving kids towards learning, even independent learning. And at the very end, I wouldn't be a curator of Khan Academy in Polish if I were not creating videos by myself. So almost 1,000 videos they are not as popular as Khan Academy videos, but they resonate among teachers. And of course, on the top of that, I take care about our YouTube channel of the Institute, which, by the way, has 4,500 subscribers, which is not bad as you consider a channel of Theoretical Physics Institute. And we don't show their videos about nice kittens, but just seminars. Yes, thank you very much. By the way, this paper Krzysiek was mentioning, yes, it took us more than a year to get it accepted in Science Advances of Science Advances. And this is a paper together with people from Nensky Institute. And surprise, surprise, it's about learning, but by mice. Thank you.
Okay, thank you, Lech. Okay, there are questions. Oh, many questions. Wow.
Okay, thank you for a very nice talk. I have a very practical problem. My daughter is in her fifth grade, and learning mathematics is mainly about learning recipes and algorithms for certain concrete things like multiplication, multiplying integers. Can you really, at that level, show any kind of deeper mathematical thinking or any problems which... It's neither...
Yes, you can. You can calculate on your own the sum of numbers from 1 to 5, right? It's 15. Now the question is, what is the sum of numbers from 11 to 15? And you probably immediately turn on the Gauss formula from sum of numbers from 1 to 15 and subtract the sum of numbers from 1 to 10. But imagine that 11 is 1 plus 10. 12 is 2 plus 10, 13 is 3 plus 10. So the sum of numbers from 11 to 15 is the sum of numbers from 1 to 5 plus 5 times 10. And this is this kind of problems which you find in a book by Bednarczuk and Bednarczuk, Mathematical Stars, Matematyczne Gwiazdki. I strongly encourage you to buy this book and let your daughter involved in thinking about it. I use it. This is basically the only book with such problems available in Polish, I think, but it does really miracles. I see this when I convince parents to buy a child this book and to work a little bit around it, and kids are really start somehow lighting up. Matematyczne Gwiazdki, Bednarczuk i Bednarczuk.
Hi, thank you for a cool talk. So I had two questions. The first was a kind of stupid practical one. How old is 6th grade in Polish? Because I don't know when they start school in Polish.
I think it must be something around 11.
Okay, cool. And my second question...
11 or 12.
Yeah. Okay. And my second question was about, did you mention mice at the end?
Yes.
Learning in mice, okay. This sounds interesting. Can you say anything more about this paper? Or?
Yes, of course. That's, we had a project, a common project a few years ago with Nensky and Warsaw University of Technology in optogenetics. And this outcome of the project was a special electronic cage, ecological electronic cage. I even held a patent on that together with people in Nensky. And we used this ecologic electronized cage, which measures position of every mouse, etc., and its orientation in space, etc., in order to understand how do they learn from social interactions. That was the essence of the paper. It took us more than a year to get it through the Science Advances, but we did it. And about 3 iterations of this experiment.
I wanted to ask you about your experience, the difference between this kind of problem-solving oriented learning and the standard what we have currently at schools and the time constraints on both, because it's a case for many years now that students finish high school and, for instance, they have less and less mathematical curriculum, so then the professors at the universities have to extend their curriculum. And I imagine that the problem solving is definitely much better, but I think it would also take more time. And if you would like to implement that in our normal schools, wouldn't that mean that we can teach better, but less things? Like, what's your experience on the time constraints that we have?
My experience, my position on that is that enforced learning is good for machine learning and artificial intelligence, but not for humans. If they are bored, they will not learn. You have first to ignite them, right? And then you may impose learning which contains certain rules and procedures and schemes, etc., etc. But it is always advisable to give them a chance to understand what they are doing. It's like long division. In Poland, it's taught as a set of rules, but long division is deeply connected with the position, meaning of the position of a digit in a number, etc., etc., etc. And therefore, and besides, we live in those times. In many information people repeat can be get from internet. I agree with that, but the essential problem is kids have to know what to do with this information. So we can slow down a little bit. We can teach less recipes and algorithm in grammar school, a little bit less in high school, but deeper, and then let our colleagues at university to earn their bread and butter, right? And even after university, if you are a PhD student, you learn a lot. In addition, this is life. If you have to achieve something, it's a lifelong learning endeavor. We don't have to be in a hurry to put as much as we can in the first, 3 years, then they are remotely capable of abstract thinking, because it has opposite result. They stop thinking.
Thank you.
But this is not very popular point of view.
Okay, let's thank Lech again for the presentation. So this ends the first part of the session. I would like to invite everyone for a well-deserved coffee. And please be back 10 to 12. Thank you. So we can start the second part of our session. The first speaker is Katja Sagerschnig, and she will present the achievements of the group of Paweł Norowski.
Yeah, okay. So, I forgot. So, move here. Yeah. So our group, first of all, let me briefly say what our research topic is. So it's more of a mathematical group. So the main area of research are geometric structures in physics. And more specifically, like from a mathematical point of view, most of these geometric structures that we're looking at are what's called Cartan geometries. That is, they have a description in terms of a bundle and a connection which has a curvature that leads to local invariance. And more specifically, particular structures we're interested in are, for example, conformal structures. So all of the people coming from GR would be interested in conformal geometries and also geometries of distributions. And so now, let me briefly introduce our group. So our group has become smaller again. So the group leader is Paweł Norowski. Then there's me, and I've also listed Jarosław Korbicz, who was part of the group. He's now at UC Davis. Okay, so now here's a list of papers published. So actually the first two are published now in 2024, 5, and the other ones in 2024. Maybe actually a paper worth to talk about would be the last one by Korbicz, which is called Stress and Geometry for Isotropic Singularities, which is really a conformal geometry paper. And finally, there's also one paper where I'm part of the authors, which is only accepted in 2004, which is called Conformal Structures with G2 Symmetric Twistor Distributions. And I'm mentioning it also because I'm planning to talk about that one. Now, concerning achievements, so 2004 was the last year of the Greek grant. So that was a grant together with our Norwegian partners in Tromsø. So the principal investigator was Pavel Norowski. So that was a collaborative grant, and it ended in March 2024. And so say at the end, for the end of the grant, we still had a final meeting in Paris. Okay, and okay, so what I didn't mention, yeah, okay. So that's about our achievements. And okay, so now let me briefly talk about the one paper I wanted to present. So that's a story that I've been talking about here before, or even Pavel has. But let me briefly review the main motivation for the paper. So it's as follows. So if you look at two surfaces, so that it comes from look at some non-holonomic systems, like you have two surfaces rolling on each other without slipping and twisting, then the configuration space is a 5-manifold, and rolling motions in that space would determine your rank 2 distribution on that 5-manifold. So they're all everywhere tangent to a certain rank 2 distribution. And in general, this rank 2 distribution will be maximally non-integrable, which actually tells you that you can go to any configuration in the system by such a rolling motion. Okay, so that's what we call the rolling distribution. And now there's a interesting fact. So if you now take the simplest surfaces, take two balls, they roll on each other, one on another, and so they can have different radii. Now, as long as the radii are different, this distribution will be such a non-integrable distribution. Turns out, and there's an obvious symmetries algebra of the distribution. It's SO3 times SO3. Now, the point is, if the radii of the two balls are 1 to 3, then the infinitesimal symmetry algebra of this distribution suddenly jumps. Instead of 6 dimensions, it suddenly has 14 dimensions. And the algebraic structure of the symmetry algebra is also interesting because it's the exceptional Lie group G2. And that's a classic effect. It's known, it's due to Bryant, but it's essentially in work of Cartan. Okay, so maybe already here, Pavel asked the question, if you are someone who likes to touch things and like to calculate, maybe that works also for other surfaces. And then he found other surfaces, so like surfaces rolling on a plane that lead to G2 symmetric distributions. Moreover, you can actually interpret this construction in a different way, namely, if you think about it, so we had these two surfaces. Now, another way of getting to the distribution is you have two Riemannian surfaces. Now you change the sign of one of the metrics and take the product. What this gives you is a metric of split signature, so plus, plus, minus, minus. And there's another way of interpreting this configuration space. You can interpret it so if you have such a split signature conformal split signature structure, you have totally null planes. And now you look at the bundle of all of this. You take a look at the bundle of all of these null two planes, so two of them. So you take the anti-self dual ones. That's naturally equipped with a rank 2 distribution. It turns out in the rolling case, this rank 2 distribution can be identified with the Twistor distribution. It's called Twistor distribution because actually this construction for conformal manifold appears also in Twistor theory. Yeah, except that in Twistor theory the distribution would be integrable, but here we are really looking in the case where it's non-integrable. And then you can ask the more general questions, namely, okay, so now you have your conformal structure again. Can you get G2 appearing as the symmetry group of your distribution upstairs? And for what conformal structures will you get Twistor distributions with G2 symmetry? And now that's what our paper is about. So our paper is first of all, okay, there's examples known, but if you want maybe to classify, then that's sort of a classification result. We have a full classification, so I should say we classified in the homogeneous case, because this allows us to use algebraic tools. But so we arrived at a classification result, and if you look at this result that we have here, so the first two structures were already discovered. Also the last, not the very last one, but this one is the one that corresponds to rolling. And then we found two more structures. Actually, one of them is a family of structures, and that's what I wanted to talk about.
Okay, thank you. Any questions?
I have a very naive question. Can this special ratio 1 to 3, can it has any connection with robotics? Because in robotics we have often rolls rolling over rolls.
You mean like connection?
I even remember when Nurowski gave a talk, he mentioned that what he's doing is related to robotics.
But I don't think that anyone uses this fact that the symmetry is suddenly G2 and the special ratio in any application. I don't think that this is the case. So no, somehow. I mean, like in principle, yes, but this particular topic, I don't think so. Yeah, this is rather, yeah. Yeah. Or you should ask Pavel, but yeah.
But maybe it makes sense to use this for some applications, right? I mean, if you have developed the theory.
But I mean, like, here's the question of, I mean, I doubt it. It's like, okay, maybe, I don't know.
Okay, thank you.
So yeah, maybe, yes?
I have a question, I guess maybe tangentially related to the idea of applications.
Yeah.
So you said the ratio of radii 1 to 3 is different and special.
Yeah.
Is there anything different and special about radii that are like very close to 1/3, but not exactly?
No, it's always, it's really,
exactly 1/3.
It's you have 6-dimensional symmetry, it's SO3 times SO3, it's always SO3. And actually should also say globally, yeah? Symmetry is SO3 times SO3. That's the infinitesimal symmetries I'm talking about, yeah? No, it's jumps. And it's algebraically, it's sort of, I mean, there's a curvature that vanishes at some point. And as soon as this curvature vanishes, because that's the maximal symmetry you can have. Yeah? So, yeah.
Yeah, I have one very technical question. So if I remember well, when I take, I just wonder, because like with those exceptional Lie groups, the algebra, sometimes some of those accidents maybe can have some like deeper meaning. So I remember that when you take SU2 representation, like 6 copies of it, so spin 3, then then SU2 or SO3 is like has G2 algebra as a as a superalgebra.
Yeah. So
is it related?
So this one is SO3 times SO3 is contained. Yeah.
Yeah.
No, it's SO. Yeah. It's.
I mean, like SO3 is contained in
how is it?
G2.
In
that representation, which is I think of dimension 7. Is it related? Because again, like SO3 appears together with G2.
Yeah, you have. Oh God. Yeah, it has to be. No, oh God. I can tell you afterwards, just not now. Yeah, I can tell it to you afterwards. I can answer your question. Yeah, but but it's, yeah. I mean, yeah, I should say. Yeah. You have? Okay, I would be happy to also, like, I'm not saying that I would want to always work on G2. I'm happy about this because this paper has been around, like this idea has been around for 10 years. I wrote this in my Polonaise grant. It's like, there's a finished paper, and it has been accepted even, yeah. So, so I'm happy about it. It's like, yeah, but yeah, it doesn't have to be always G2, yeah. Okay.
Okay, so let's thank Katja again. And I would like to invite Michał Oszmaniec, who will tell us about quantum computers.
Does it work?
Someone left his or her mobile. Please go ahead.
Yeah, so it's a great pleasure for me to present results of the statutory topic 7, quantum computing topology and geometry in quantum mechanics. So, so leader of this topic is actually Adam Sawicki, who is in China, so he couldn't present today. And we also have on board Professor Iwo Białomicki-Birula. So yeah, like as you see, the title of the topic is broad, so we do foundations of quantum computing, but from, say, computer science perspective of mathematics, physics, but also we work on topology, differential geometry methods in quantum information, as well as relativistic quantum mechanics, in which Professor Birula specializes. Right, and so technically we have in the topic 2 groups. So first is quantum mathematics group led by Adam. So they realize now this grand opus, efficient sets of gates for shallow quantum circuits. They like we have Oliver Reardon Smith postdoc there, Oskar Słowik PhD student, Piotr Dulian project student, I believe, and some an intern, Bartosz. And my group, that was a bit disrupted in last year or so because of my a bit unfortunate journey to NASC, as some of you know. But yeah, we are still, like I'm back here at CTP, and I'm very happy with that. Thanks for the support to the whole community, but to the director, Krzysztof especially. Right, so especially my main collaborator Maciej is on board. Last year we still had Susanne as a PhD student. Philip, I put him on the picture. He doesn't work with us anymore. He left to States a couple of years back, but this year he will defend his PhD thesis. And Daiki will be joining me as a postdoc later this year. I should mention also Orgert, who was a bachelor student from brilliant bachelor student from Faculty of Physics. He left studying abroad, unfortunately. Unfortunately, and in terms of project, we are quite fortunate because. Quantera project took an epic that we were able to bring back to CFT, and another European project coming in later this year. Okay, is that papers? So, yeah, so it's we have I think substantial activity, as you see. How many 15 papers. Published or submitted or accepted. Right, from 4 come from Professor Iwo Białomicki-Birula, 4 from group of Adam. I guess Jarek will be talking about this paper later. Right, what should I say? Maybe Krzysiek mentioned that, let's say, in quantum mechanics, quantum part of the community here tries to sometimes simulate larger quantum systems, and in that context I should mention Oliver, who also collaborated with me. So he works on like developing classical simulations for classes of quantum computation, so also for many-body problems. Right, and yeah, there are many papers, different topics. I want to talk about this single one that I'm fond of. It appeared in PRX, so let's jump into the meat. Right, so it's a joint project with Maciej that I already mentioned, Michał Oszmaniec from Gdańsk, and Nick Hunter-Jones from Austin nowadays. Right, so it's the paper is about saturation and recurrence of complexity in random quantum circuits. And I know we don't have, like, we come from the, so basically I don't have time to, paper is like 50 pages long. I just maybe explain basics, what we are doing in it. So what I mean by complexity, either classical or quantum. So classical complexity is a very primitive object in classical computer science. So imagine I want to perform some computation, so some transformation of bits, okay, say reversible transformation, and complexity for me would be the minimal number of elementary gates that are needed to realize such a transformation. Okay, so the more such gates are needed, the harder it is for me to realize it in practice. Yeah, quantumly situation is similar. So I have now not reversible function, but unitary that acts on n qubits. But what I now want to do, I want to approximately perhaps realize it as a sequence of gates, of some primitive gates that act on my system. Okay, and the minimal size of the circuit, minimal number of gates, I call complexity. Okay, and those are very important concepts. Okay, why? First of all, because when we talk about just like classical or quantum efficient computation, they are just expressed in terms of unitaries or functions that can be computed via polynomial size that have polynomial size complexity. Those terms are used to classify phases of matter, and also these days find applications also in like many-body physics of interacting systems. Okay, so now our work concerns this Brown-Susskind conjecture that I want to now introduce to you. So it comes from two physicists, Brown and Susskind, and it concerns a very basic problem, namely how complexity of a unitary or a state changes with time. So I have some Hamiltonian, some isolated quantum system that evolves according to some interacting many-body Hamiltonian, and I am interested in like how complexity of this unitary changes with time, because maybe I would like to simulate this evolution on a quantum computer, right? So like for example, because of that. And like those two gentlemen, they came up with the following conjectured behavior of this evolution. So remember, I have n-body system. It evolves in time. And then we can separate three phases of this behavior. Linear growth for exponential time up to maximal allowed complexity, which is exponential. Then saturation in the plateau, like we have plateau for now double exponential time, okay? So complexity becomes very large and stays like that until it recurs after double exponential time, after Poincare-like recurrence event that takes this much time. And there is some motivation to study this problem from the ADS-CFT correspondence perspective. But let's say for this talk, let's say this is some conjectured behavior of many-body system that we would like to have. Especially maybe this linear growth is interesting because, let's say, it shows that there are no shortcuts in complexity when we want to, when we want to simulate quantum dynamics on a quantum computer. Okay, so this is a very hard and for me, okay, fascinating and like, important problem. It's like, but people cannot like address it nowadays. So they substitute Hamiltonian dynamics via random quantum circuit dynamics, which is another model of chaotic system. Okay, so instead of unitary evolution, we have now evolutions that are just generated by random quantum circuits. So we have now discrete time, and at every time step, we apply some random 2-qubit gate that entangles our system locally. Okay, and so we choose pair of qubits at random, and then apply some random gate here, and then we continue. And we have the same, really like the same conjectural behavior for this model. But it wasn't proven, really, until, I think, recently. So previous works by, okay, for example, Brandao, Michał Oszmaniec, and others, they showed some early time polynomial growth of complexity. Okay. Then 2 years ago or 3 years ago, there was some nice work that showed linear growth, but for unphysical complexity, which required exact computation of unitary, okay, by Jonas Hefferkamp and others. Just last year in the autumn, there was very nice work that finally proved linear growth for some exponential time. It's considered a breakthrough for the field. It appeared in many conferences. It's related to designs, to approximate designs, and yeah. Okay, so where we come in? In our work, we focused on late time behavior of complexity, and in this model we proved saturation after exponential time, recurrence after double exponential time, and we proved like duration of recurrences. And tools that we used to prove that came from the theory of random walks on manifolds, high dimensional probability. Yeah, so I'm about to end. Okay, we also studied like continuous time version of the model, some stochastic local Hamiltonian dynamics. Okay, so in a nutshell, what we did, we used spectral properties of those random walks, like spectral gap property, to show that after exponential time, on some micro scales, like distribution of this random walk mimics that of Haar measure, but it's not exactly Haar measure, but it mimics its properties. Okay, we call it approximate equidistribution, this property. And basically, just from this property of approximate equidistribution, we could prove those saturation, recurrence, duration of recurrence. So it's like some universal prescription, which, yeah, like it doesn't depend on details of the model. So just this property is important. And right, so I just wanted to conclude with just mentioning some open problems. So we want to maybe study it for Hamiltonian dynamics. And yeah, let's say that's one of the key things we are currently working on these days. We have some partial results, but not for physical models. So I think I should finish now. So thanks.
Thank you, Michał.
Okay, so the conjecture you are proving here, it's not formulated in a very precise way. I suppose that what you mean here is that there is some kind of typical set or typical type of problem you can attack, and for this typical problem, this is what you expect. Because you can imagine some kind of specially arranged types of systems or channels which are very easy to compute for for all time.
Right. So it was formulated by physicists, so it's not very rigorous. Okay. For me, I would be so the goal would be to prove it for some physically motivated ensemble, say of random local Hamiltonians, like two few body interactions, some random coefficients, things like that. Let's say, yeah.
In classical physics, this reversibility, which you call recurrence, is connected to the Poincare time of reversal. Is it same?
Right. So actually, we are currently working on. There was, of course, work, quite substantial work, for example, by Peres and others about recurrence times in Hamiltonian dynamics, but we checked carefully those works, and they were like. Basically, they had flaws, and now with Maciej, for example, we are working on to close those gaps and to have quantitative statement about recurrence times. But you are perfectly right that when you return to the initial state, like initially, let's say initially your complexity is small. So if you come back in the vicinity of the initial state, so that's the explanation of the second part. So it's related to this. But the point is to give quantitative estimates on that.
So may I ask another question? But if it's related to some stochastization, then different Hamiltonians, they result to different stochastization. Some of them just do not stochastize, and they don't produce any thermalization or stochastic process. But you are talking about some Hamiltonian, but didn't specify if they are.
Yeah, so I would perhaps have like non-commuting. Yeah, it should be. You should have many non-commuting terms. I agree that one can cook up quite easily examples where this won't hold, but those would, I would say, probably would not be genuine quantum Hamiltonians. But I agree one should be very precise what one means, and of course, in case we make some progress, we would formally say for what classes of Hamiltonians we can give results. Yeah.
I have a very naive question. What physically sets you this recurrence time? Is it a finite number of elements in the system? Because if it is infinite, you would have to wait infinite amount of time for configuration to reappear, right?
Right. So physically, it has to do with dimension of the, let's say, with the size and dimension of the system. So when we have n-qubit system, and we discretize it, because notice that I wanted to have discretization scale and epsilon. Like basically, how to put it? You are certain, as a previous question suggested, that after some time, you'll be, just from some general results in dynamical system, you'll be in the vicinity of the initial point. If you don't converge to some stationary point, which is like the case for the classes of dynamics that we are after. So basically the size here is finite, and that sets scales, maximal scale of complexity, as well as how you about also the scales of recurrence.
What is meant here by the chaotic Hamiltonian? Is it still the same Hamiltonian that we teach students about? Is it the Hermitian operator that is acting in some Hilbert space?
Yeah, so it's a Hermitian operator. Yeah, so I should say that, so it's not very precise in the field what is meant by chaotic Hamiltonian. So for example, we do have a work that I even quoted here with Maciej and Michał, Maciej Kotowski and Michał Chorodecki, where we studied paradigmatic, GUE evolution, very interacting GUE ensemble, and you don't have such a behavior. Instead, you have a jump. Like very suddenly, you jump to like maximal complexity. We proved that.
So there is no Hermitian operator
Oh. No, there is. There is.
So what makes it chaotic?
Pardon?
What makes it chaotic?
What makes it chaotic? Yeah, well, of course, yeah, so how to put it? Yeah, so it's maybe about like syntax, like, so in the field, by chaotic, people probably mean, people tend to say, what is, like, they specify some features like level repulsion or spreading of correlations. It's not very, like, precise rigorously, but for me, chaotic would be, sure, but, right. Yeah, so, but here, this conjecture, okay, you see this graph. This graph is rigorous. It's for paradigmatic Hamiltonian evolution coming from GUE ensemble. You don't have such a behavior. And the reason is you don't have locality in your Hamiltonian. So basically, for me, chaotic would be some generic many-body Hamiltonian that is nevertheless local with respect to constituencies of the system. Yeah, sorry, Professor, I cannot, like, I can just refer to the field and status of the field. It's not, I think it expresses good intuition, but it's not extremely rigorous.
Okay, the last question.
I might be completely wrong, but I have this association with this first part of your plot, this raising until the saturation is acquired, with something which is called formation time in quantum mechanics. That is, you have complicated Hamiltonian, the system becomes sensitive to, is able to resolve states which differ by energy level differs by a small amount of delta E only after time which is inversely proportional to this inverse of 1 over delta E. Mm-hmm. The phase difference has to accumulate to be, quote unquote, at least 2 pi, right? Whether before that, those two closed states act basically as a 1.
That's true, but I guess that would be maybe about very initial stage, and that would be about whether you escape the initial point, maybe. And here it's about like compiling the whole unitary or approximating the state via sequence of gates. So maybe at the beginning, but after maybe linear time, it may not be like this anymore, I guess, yeah. Yeah, linear, but I think what you say might probably just touch like really very early times, but later it's a bit more subtle. I'm happy to discuss later.
Okay, let's thank Michał again.
Thanks.
So the next speaker is actually me. Pointer is here. So I'm Remigiusz Augusiak. Hello, everyone. I'm responsible for task number 8, which is non-classical correlations in composite quantum systems. Well, this is the structure of the group, my quantum information group in 2024. There were as many as 6 postdocs. There was some rotation. Now I have 5 postdocs. There were 2 PhD students who defended successfully their thesis and left, so no PhD students in the group at the moment, which is quite sad. Then I experienced during vacation a whole invasion of students, so there were like 9 of them. So now there is 6 associated to the group. One defended his bachelor at the University of Warsaw last year, and there are 2 others who are preparing their bachelor thesis with me at the moment. But I must say it's, well, actually very nice that the students come because they can solve problems, and it's enjoyable to work with them. Okay, these are the topics that we are doing. So, well, we do mostly the same every year. And the funding is, I have 2 NCN grants. One is Sonata BIS, which is a larger project. Then I also have Quantera project, which is a small one. Then I managed to get on board of a European project through the HOPON facility. And I noticed quite sadly that this year this will not be continued, this facility. And there was also this Pacific Cofund project by Sheikh Sazim. This was his individual project. This is the production of the group. I mean, the papers that we managed to publish, and there are also some preprints from last year. And I'm going to talk about this one, which was prepared with Ignacy Stachura, who was a third-year student of physics at the University of Warsaw. Ignacy is still with the group, kind of. He did his bachelor's with us, but then he moved to medicine, and then after studying medicine for 1 year, he gave up, and he's back to physics now. And he's pushing me to work with him. Okay, in any case, this is the problem. So I'm going to introduce a couple of definitions, and then I will state the problem, and I will explain the solution. So we consider a multipartite quantum system, multipartite pure state. And then we call this state genuinely multipartite entangled if it cannot be written as a tensor product of two other pure states with respect to any bipartition of the whole system and partite system into two subgroups, let's say, which are disjoint and non-empty. So if you are not able to write a state in this simple form, then it means that the state is genuinely multipartite entangled. And here at the bottom of the slide, there are two examples of such states. The first one is the famous GAZ state, and the second one is the less famous W state. You can check by hand that they cannot be split in any tensor product. Then another definition is that of the genuine multipartite non-locality. So let's imagine that we have the same state, but now each party can perform some measurements on their shares of the state, and they obtain some outcomes. The correlations that they observe in the whole system are described by a collection of probability distributions. This is the standard Bear scenario, the standard Bear experiment that people consider in the literature. Okay, and now this correlation, we call this collection of probability distributions correlation. If the correlation cannot be written, okay, it should be not equal here, I made a mistake. If cannot be written in this as a convex combination of probability distributions that are product with respect to some bipartitions, then you have to include also the convex mixture over all such bipartitions. If it cannot be written like this, we call it genuinely multipartite non-local. So we have two notions now, genuinely multipartite entanglement, genuinely multipartite non-locality. And the task is to compare these two. And our task was simple. We wanted to prove the so-called Gisin's conjecture. Gisin's conjecture says that any genuinely multipartite entangled state is also genuinely multipartite non-local. Very simple statement. And so here I also write it more explicitly. We take as a pure state, which is genuinely multipartite entangled. We perform a Bell experiment on it. We get correlation. And the question is whether this correlation, whether we are able to obtain correlation from a genuinely multipartite entangled state that is genuinely multipartite non-local. This is a very simple question. Okay, and it's true in the bipartite case. It was actually proven by Gisin, and then it was continued by some other people as well. And then it's also proven for some multipartite states. It's actually known that every pure entangled state exhibits some form of non-locality, but it's unclear whether genuine multipartite entanglement implies genuine multipartite non-locality. And of course, in the other direction is true, because if you observe genuine multipartite non-locality, it means that the state must have been genuine multipartite entangled. Okay, and why we ask this question? Well, it's a natural question to ask if you want to understand these two notions. And in quantum information, entanglement and Bell non-locality are considered different resources. So the question is how they compare to each other. So entanglement is a resource in the so-called device-dependent quantum information. And with entanglement, you can do, I don't know, quantum teleportation. Bell non-locality is a resource in device-independent quantum information, where you don't have to make assumptions about the devices used to perform a given task. So it's perceived somehow a stronger notion than entanglement. You can think of Bell non-locality as device-independent entanglement. You can associate many names to that. It doesn't matter. Bell non-locality is useful for some things. And actually, a month ago, we had a nice talk of Tony Yasin, who was inventor of this notion. We had a nice talk in Warsaw at the University of Warsaw about this type of notions. Okay, so what we have done with Ignacy, we took a paper by Florian Kurschot, my former collaborator, they introduce a quite general class of Bell inequalities that detect genuine multipartite non-locality in multipartite systems. And they provided a lot of evidence, numerical evidence, that these inequalities might be useful for solving the Gisin's conjecture, for proving the Gisin's conjecture. So, when the student approached me, I said, okay, let's try to work on this because maybe we will prove it. This problem is very difficult, so many people have tried and failed. Okay, I was thinking that maybe students will do it. So they introduced a couple of inequalities. Here I present the simplest one in the tripartite case. So we have Alice, Bob, and Charlie. They perform measurements, they observe correlations. And now, if they are able to violate this inequality, the simple inequality, then they can certify that the correlation that they obtained in the experiment is genuinely multipartite non-local. This this expression here is the CHSH, closer Horn-Shimony-Holt famous Bell expression. Okay, so we have a sum of two that somehow check correlations between Alice and Bob and Charlie. Okay, so we were struggling with these inequalities for almost a year and trying to prove the Gisin's conjecture. We failed, but then suddenly the smart student discovered that these inequalities can be seriously improved. So we started to work on this again. So we provided some generalization of the method of Florian Couchot and collaborators that allows us to get better Bell inequalities. And these inequalities are really promising if you would like to prove the Gisin's conjecture. Then we managed to prove the conjecture for the simplest 3-qubit case. And that was this is the end of the story, because it seems that if we go to more parties, the problem becomes very difficult. Now we are trying to do it, to solve it with another student who is also interested in this type of question. Okay, so this was the proof, how we prove it. Okay, doesn't matter. Let me conclude. So what we have obtained with a student is that a general construction of Bell inequalities detecting genuine multipartite non-locality. And we also managed to prove Gisin's conjecture for the simplest tripartite case with a single Bell inequality. So the take-home message from this study is that we have a good inequality. It seems that we have a good inequality to prove the Gisin's conjecture in any case. But okay, I mean, how to prove it is unclear. And the second main message is working with students from undergraduate students is enjoyable and can benefit us a lot. And I would like to invite you. I would like to invite you to approach on my postdocs because they prepared some posters. So during the lunch break, please discuss with them. Okay, thank you. Questions?
So this field seems to be, from mathematical perspective, down to proving inequalities in this type of product tensor spaces. I wonder, how is it possible that students whom you have know mathematics of this type of algebra and mathematics of this type of spaces well enough to produce some meaningful output? I'm curious what kind of people they are.
Well, I know how to answer it. So I give them papers and provide some literature. They read, understand, and they are able to work on this. I must say that I have had already several students from the University of Warsaw and also from the, how it's called, Technological University of Warsaw. And they're really, really smart. So yes, this is what I can say. And that's why it works.
Yeah, I have a technical question. So you used, I guess, the form of equivalence class of LU equivalence class of 3-qubit states. If so, was it like crucial in your proof, or like if you had such a form for higher number of particles, would it benefit?
Yeah, so we use it. Let's say it's crucial, but I don't think it's so crucial that you have to have it. And it's the paper that I had on a slide has this form for any number of qubits. Okay. Any other question? Okay, so let's thank Remik again. And the next speaker is Jarek Korbicz, who will tell us about pointer states in the Born-Markov approximation. I think it will be a talk about the PRL paper that was published last year.
Thank you, and the pointer. Thank you very much. Thank you, Remik. I'm reporting on the last year progress of my micro group, which is a group on open quantum systems and quantum foundations. The members of the group, Tae-Hoon Lee, who has been a PhD student with us, and he successfully defended his PhD thesis early this year. Rajendra Bhatti, a so to say fresh postdoc who joined I think October last year. Tomek Bazylewicz, he is a master student from the Warsaw University. Past member Masaya Takahashi, who was a postdoc for a year with us, and then left April last year when the funding finished. The funding, I'm sorry, I did not put the grants, but the funding last year, it was the last year of my Opus grant, from which Tae-Hoon and Masaya were founded. That was the grant on the studies of objectivity in quantum mechanics. Last year, we also started a Quant-Era grant, and Rajendra and Tomek are paid by that grant. And this is a grant aimed at studying of the effects of quantum decoherence in quantum algorithms. Okay, so let me see if it works. Okay, the publications last year, what was published, so there was one PRL which I will present today. It was published somewhere early last year. Of course, the work was done earlier, but I decided to present it today because I think this is something that can be told very easily in about 10 minutes. Then there were a bunch of other papers, mainly with Tae-Hoon, that were the basis of his PhD thesis, and also one paper with Arizona bunch, Jan Ver and his at the time PhD student Alberto Acevedo. There is also a couple of interesting results that we obtained last year. Hopefully they will be published this year, so I will report them next year, including a hypothetical gravitational decoherence mechanism. So now to the core. So the question which we actually successfully answered in some sense. I mean, you will decide in how successfully we answered it. The question is the one actually that looks innocent, but which gives the meat, so to say, the physical sense to the whole decoherence theory as a physical process. Namely, the question is into what mixture does the wave packet collapse? That's an old question of Wojtek Żurek that was asked by him in the beginning of the 80s. Well, the problem is the following: that if we have access just to the local state of some system that we observe, so how come that in the macroscopical real life situations we have something that seems like a preferred basis? For example, positions are well defined, and we have to sweat very hard in order to get superpositions of positions. Yeah. So how come that there is a preferred state of basis which seems to be singled out, at least in the macroscopical situations? This preferred state are called the pointer states. And the great idea was that actually there is a sort of explanation why we observe them, and this is a physical principle which is called dynamical stability. Namely, these are the states that survive the, so to say, survive the evolution with the Hamiltonian. So they are dynamically stable with respect to the Hamiltonian. Okay, so this is actually the physical principle which makes the decoherence, which up to until that moment was more or less viewed as a sort of like a mathematical artifact. This is something which gave decoherence actually a physical meaning. So there is a physical principle, this dynamical stability, which singles out in the set of states in which we expect the system to be after the end of the decoherence problem, the coherence transition. So, great, looks nice, but in most situations, of course, this is not what happens. I mean, in most situations, the dynamics is so complicated that there will be no set of states that can that will be preserved by the dynamics. Okay. A simple example is so-called quantum Brownian motion, where we have a central oscillator which is linearly coupled to a thermal bus of oscillators. There is nothing like this, because the self-Hamiltonian of the system will drive the eigenstates of the coupling observable, will drive away from the eigenbases. Okay, so there was another. Then there was a question. Okay, so how to substitute this nice and beautiful but highly idealized dynamical stability with something more relaxed and yet having some sort of a physical sense, or at least physical appeal. And then there is an idea which is called predictability sieve, which says that the states which will be the closest to what we call the ideal pointer states would be those states which generate the least entropy during the open evolution. So the setting is the following. I initiate my system in some pure state. I let it evolve, interacting with the environment, and after some time, I look at the state and I ask how far away is it from a pure state. Okay, that's of course very much a relaxation of this condition, because here it's not only the state's pure, but the state stays the same. But at least let's ask for something minimal. So how to pick the states which generate least noise, so to say, during the evolution, during the open evolution. So one can characterize all that very nicely mathematically. Namely, one can introduce something which is called linear entropy, which exactly is the quantity used in quantum information and foundations, which measures how far away a given mixed state is from a pure state. So this quantity is zero if and only if the state is pure. So the projection on the vector. And now you can ask, for example, what is the asymptotic, there should be 1/tau here. What is the long time average of this entropy production, okay? And the relaxed version of this dynamical stability says that the approximate pointer states are those states which generate the least entropy, so they are the least mixed in the long time. So now the question is, okay, how to find them? There was one prominent example from the 90s, so the quantum Brownian motion, which I said this is an oscillator coupled to a bunch of oscillators. And then the very nice result and very like a physically appealing result was that the approximate pointer states are actually the usual Glauber-Sudarshan coherent state. And of course, there was a whole picture being drawn that there is a competition between, as you see here, the coupling is via positions, okay? And the self-Hamiltonian has the momentum, so of course this does not commute with this. But then somehow the picture was that, okay, but there are those compromise states between the eigenstates of position and momentum, and these are the coherent states, and we believe that they are the most stable. That was a very nice picture in the quantum Brownian motion. It was then studied also in Lindblad formalism. what we did, we tried to answer the question, what are those approximate pointer states in much broader family of systems, namely the systems which are described by the Born-Markov approximation. Okay, there is an ugly-looking equation of motion that one can derive for a state of the system in interest interacting with the environment and satisfying the conditions of Born and Markov. And we were asking, okay, so which are the pure states which generate the least possible entropy, so that they get mixed to the least extent because of this evolution. We had to make some assumptions. So basically, we wanted to generalize this result, which is one of the emblematic results in the whole decoherence business. So we wanted to generalize this result that was obtained in the very specific model. We wanted to see, can we do better, and can we generalize it to something more? And in particular, is it true that coherent states are those approximate pointer states? So we studied the Born-Markov approximation, which is a very powerful machinery. It has its own moments. It's not possible to guarantee the positivity of the state for all moments, but this is an approximation. But anyway, we took it as the starting point. We assumed some group theoretical assumptions on the structure of the Hamiltonian and the coupling observable. And quite miraculously, after a little bit of sweating, we were able to derive an equation for asymptotic entropy production in this Born-Markov setting with a group structure. Okay, that was quite actually quite unexpected, that under a pretty, I would say pretty general, I wouldn't call them mild, but under a pretty general assumptions that there is a group and with associated Lie algebra and the coupling observable, the self-Hamiltonian of the system, the coupling observable, they come from that Lie algebra. For the purpose of this work, we took the group to be compact semi-simple, just to have a simple structure of the Lie algebra, but the method can be actually extended to other groups. And after quite some sweating, we got a very ugly looking, but still a quite a well-defined equation, which describes the entropy production in terms of what you see here. These are the variances of basically of the coupling observables which enter the model, and there are also reproducing itself the damping coefficients, which we know very well from exactly for example from quantum Brownian motion. Now maybe I will skip the details. I have 3 minutes. Okay, very good. I'll try to finish actually quicker. So one can study different regimes, like for example, high temperature, low damping, high temperature regime. When those entropy production equations, they take a very simple form. So this formally this equation looks actually like a group invariant dispersion. Which is actually the defining quantity for the minimum uncertainty states. This is well-established knowledge from I think the Ascott-Perry-Womov book is the absolute reference here. So this looks formally the same, but there is one big and crucial difference. Namely, here this is the so-called Killing-Cartan metric, while what we got was some positive tensor, but its in general, it is not the killing Cartan form. So one of the messages to take from here is that actually there are two, so to say, there are two notions of being the closest to the classical. There is one which is kinematical, which is defined by the uncertainty relations and the well-known procedures involving killing Cartan form and all that machinery very beautifully described, for example, in the Piriwomov's book. And then there was also the second notion, which is the dynamical notion, where we have a system interacting with the environment, and we want to ask, so which are the states of the system that sort of like survives the interaction with the environment with the least impact. And it was sort of believed that these two notions coincide, but actually we showed that they coincided for quantum Brownian motion model because of some peculiar group identities which lie behind that model. But in general, these two notions, the kinematical and the dynamical, are different. Examples, so we studied for spins. And actually, for spins, we found, and of course the problem is, okay, so great, we have this ugly-looking equation. So how do we find solutions? So how do we find pure states which will minimize the right-hand side of this ugly expression? Well, this is the question to all of you. I have no idea. Even this equation looks very simple, but I have no idea how to solve it in general. With Uttam Singh, who was at the time a postdoc with me, we managed to solve for spin-spin systems. It turned out that the state which we get is very close actually to the so-called spin-coherent state, but not exactly the spin-coherent state. There is a small deviation. And unfortunately, this is so far the only example of the solution of the equations that we got. So I finish here with the appeal that you have heard many times. I have a contact to the Ukrainian soldiers in the front. If you want to help, especially now when the US changed side, this is very important. If you want to help, please contact me. Thank you very much.
Thank you, Jarek. Any questions? Michał, any questions?
Okay, maybe I missed that. What actually depends on what you assume about this environment? Because I think it's kind of crucial. I understand that the behavior of the system somehow has to depend on what you assume about the environment itself.
Well, there is a whole list of assumptions about the environment. So first of all, the assumption is that here this is the general assumption. It's called Born assumption. The assumption is that the environment is big and inert, so big and inert that it actually does not feel the presence of the system, but not vice versa. The system feels a lot the presence of the environment. Then the second assumption is this Markov assumption, is that the environment, in a sense, is fast enough so that it has no memory. Then there is also an assumption that the coupling between the system and the environment is via some observable, for example, position or momentum. I call this observable A here. And then there is another set of assumptions which comes with a particular structure, how the observables, so the Hamiltonian and this coupling observable, how they look like, and that there is a group, and those observables are expressible via the Lie generators of this group. Yeah, so there is like a whole list of assumptions. Some of them are pretty standard, this Born-Markov. It's like the classic of the field. And then we added on top of that some pretty mild group theoretical assumptions.
Okay, any other question?
Yeah, I can always ask something. So I have like a fundamental question. So you studied this entropy production and you wanted to minimize it. So my question is, like, operationally, can you, like, because this is a mathematical, like, principle, right? So you would maybe expect that states that are stable would have minimal entropy production in some sense, but in practice, do people observe something like this, like because you would like to, if I understand well, mimic the process of measurement via this open system dynamics?
It's a very good question. It's a very good question. One can sort of like debate it. So, is this minimum entropy principle, is it enough to reproduce what we see in the reality? I'm not sure how to answer. We just answered my much milder question. So how to solve this minimum entropy production? But then it would be next step to try to make some physical sense out of it.
Thanks.
Okay, let's thank Jarek again. And the last speaker of our reporting session is Maciej Bilicki, who will present the results of Computational Cosmology Group. The stage is yours.
Good afternoon. So it's the last talk, so I will try to be quick. I will present the achievements of the Computational Cosmology Group in 24 and discuss in more detail one particular research highlight. So this is the group as of 24 and partly 25, so the members who were there the whole 24th year are listed here. So Wojtek Helwing is the leader of the statutory task, testing general relativity and alternatives using galaxy density and velocity fields. I'm co-leading the group with him, and we have Mariana, who is now above postdoc, so to say, because she got a grant and she's not anymore a postdoc in our grants. She's not a permanent researcher, but she's something between being a postdoc and a group lead, so she has her own small group. Then we have 2 postdocs and 4 PhD students as of 24. Then there was also 1 more postdoc and 1 more PhD student last year, who left for different reasons, but the number is conserved. We have 1 new postdoc and 1 new PhD student this year. Okay. So a few highlights. A big achievement of our group was the first PhD defense within the group and also under my and Wojtek's direct supervision. Suhani Gupta, who defended in May linear and nonlinear statistics of the cosmic density field in modified gravity cosmologist, was the complicated title. We got also a big success of NCN grant awarded to Mariana, as I mentioned, which started also already last year. And we had also 2 STER research visits from the PhD school, and also Anjita got a Young Scientist Award from CFT. I hope I didn't forget any of the grants that we got. 2 grants also finished, 2 grants which Wojtek led. 1 finished formally this year, but like 3rd January. 1 Sonata Bis and 1 non-existing anymore Beethoven grant jointly with German partners. Okay, so this is the quick summary of this, around scientific things. We also were active on many fronts in conferences, etc. So first of all, large success and large achievement of our group was organization of a workshop which was called CLUES, for Local Universe Exploration and Study. So CLUES, with this acronym, is a international collaboration working on constrained local universe simulations. And we organized a meeting of that collaboration with Oliver Newton as a chair of the LOC and large part of our group in the LOC. Of course, we also gave talks on this workshop, on this conference, it's normal. And it was supported partly by the NAVA grant that Jarek was leading or is leading. We gave also many talks, I just list a few here, at many conferences, workshops, seminars. So there was a big cosmological conference in Krakow last year where Marianne and Wojtek had talks. There was also IAU, so International Astronomical Union General Assembly. It's the biggest meeting of astronomers in the world, which was held in Cape Town, and Oliver and Priyanka got talks there, but they couldn't go in person, so they gave remote talks. There was also a consortium meeting of the Legacy Survey of Space and Time, LSST. It's a survey that will start very soon. The telescope is already built, and we were also involved there. And then there were seminars. Our mostly postdocs and students as well were giving seminars in different places in Poland and abroad. We had also some membership in science organizing and local organizing committees, and there was some outreach activities. I might have forgotten some. I know about Gusha Ranjit's activities. Maybe there were some others. Sorry if I forgot about this. Then there were many papers coming from the group, but they are always a lot, especially from, for instance, me, because I'm involved in large astronomical consortia, so then I end up on long author list somehow, sometimes, on the 10th, 50th place, so I don't really count this as, output of myself directly. But there were also those which were really led by members of our group, and we publish in top journals that are of interest for cosmology, so Physical Review D, monthly notices of the Royal Astronomical Society, Astronomy and Astrophysics. And these are these papers that were led by our group. So, and you see that they were about both the cosmic web, so the distribution of galaxies on the large scales, also about some more general cosmological models, like the one led by our former postdoc, Krishna Naidu. You've heard about dynamics of pairwise motion in Mariana's talks a few weeks back. And then there was also one more paper from Suhani that she completed, I think, after PhD defense. And finally, there were also two dealing with machine learning and I will speak about this latter because I'm very proud about this paper and very happy that Priyanka in particular did this nice work. Okay, so the title here is Enhancing Photometric Redshift Catalogs for Color Space Analysis, Application to Kids Bright Galaxies. It's a paper from the Kids collaboration, a funny name, but a serious collaboration. That there's many more authors on the paper than listed here, but the three leading were from our group. And we basically had two main questions that we wanted to answer in general. So how to quantify mismatch or match between two multi-wavelength data sets, how to improve training sets for supervised machine learning using particular data. And the answers that we came up with are that you should first use an appropriate method to map this n-dimensional feature space onto 2D that you can understand with your brain, and then use that 2D mapping to combat the mismatch. And I will try to explain what we mean by that in the next few slides. So I have to give you some introduction about some of the notions here. So Kilodegree survey is a already finished survey that scanned a large part of the sky in many wavelengths, from the ultraviolet basically to near infrared. And the main science goal of this survey is cosmology with weak gravitational lensing. And actually next week we will have a main result coming up from the final data release, main cosmological result. My particular involvement in this survey is by working on what we call the Kids Bright Galaxy Sample, which is a selection of brighter end galaxies that we use to enhance the cosmological studies and also look more into galaxy physics or galaxy evolution even. The key point to understand here is that this data that I'm talking about are photometric, and by that we mean that we have measurements in various broad passbands, but we don't have spectra, and spectra are key to really do science, but because there are like 100 million galaxies in this survey, you cannot do spectra. So you have to live with the multi-band information. And another important thing here is the redshifts. So in cosmology, you need redshifts to map the three-dimensional distribution. But as I said, we cannot, and these are really exactly obtained only from spectra. But we cannot, in such large surveys, obtain them directly from spectra because we cannot follow all the galaxies. So the standard practice in the field is the so-called photometric redshifts, where you estimate those redshifts from multiband fluxes. And in particular, for this sample that I'm talking about here, we do this with supervised machine learning artificial neural networks, which, as I learned last year, is physics, because you get Nobel Prize for that, which was quite a surprise for me. I always thought it was computer science and mathematics, but okay. And we do it in particular also now with deep learning. This is what Anjita has been working on and submitted a paper this year. And supervised learning means that you train a model on data with true labels. In this case, you have labels are redshifts, so values of the redshifts that you derive from some overlapping data for which you know them, and you train a model and then apply this to your full data set. The problem with this is that supervised learning is not very good at extrapolation. If you train on some data which are not well matched to your target data, and you then apply your model, it will predict, well, normally it will just predict wrongly, but the problem is that you cannot even check it, because if you don't have the true labels, then you don't know. So this is a problem. Now, for this particular data set, we have a training set, which comes from a survey called Gamma, spectroscopic survey, so having true redshifts, which is overlapping with our general photometric survey. And we trained our networks and applied to the entire photometric data set. But this kind of surveys, spectroscopic surveys, are never complete because there are always some observational nights or some other reasons why some galaxies are missed by the survey. Spectroscopy is very challenging, much more than photometry. You have to integrate for a long time, and this is much more difficult. So we need to really use this kind of surveys for training your, for instance, photometric redshifts. You need to quantify how your training set is matched to the target set. And here the challenge is that our feature space is multidimensional, so it's at least nine-dimensional. So you cannot just look at some pictures and decide. So you have to have some method, and we use in particular so-called self-organizing maps, which is also a machine learning techniques, but it's an unsupervised one, which means that you don't train on true labels. It learns patterns in the data, and it in particular can map n-dimensional associations from your input data onto 2D planes. So it preserves topology of the input data. And here are examples of this kind of self-organizing maps. So what we do is that we build these maps from 9-band fluxes. In practice, this is much more because we also use combinations of the fluxes, so-called colors. For machine learning, you have to give sometimes redundant information. So we actually use 45-dimensional space on input. And then you map it on 2D planes. And here, just to clarify that these maps are toroidal, so the left and right edges are joined. They are like that, and also the top and bottom are joined. So there is a transition from bottom to top and from left to right. So this is just abstract representation of the data. So these maps are cells, and we chose to have hexagonal cells. In each of these cells, you have a number of galaxies which are mapped from the input data, and they are similar in some respect in the input data, formally by Euclidean distance that you measure on the features. And then you can also then color each of the cells with some property. And here are examples that show you that really this is not random organization of the data. So for instance, the fluxes which are on my right-hand side are not randomly distributed, so the faintest galaxies are in the middle. So magnitudes in astronomy go the other way around. Yes, the fainter means the largest. So also the so-called colors, so this is colored according to what galaxy really are. So the redder colors are redder galaxies and bluer are bluer galaxies. Then you can also measure total mass of stars in a galaxy. It's a very useful thing for a galaxy evolution perspective. And finally, the photometric redshifts, which I talked about, also are not randomly distributed on such a map. Okay, and this is just an example to show that you can you start from, for instance, 45 dimensions, and only some of them were used in the training. I'm not sure if the pointer works. Well, the R magnitude and G minus R color were part of the training, and all the other magnitudes which go from the ultraviolet to near-infrared, but the stellar mass and photometric redshifts were not ever used in mapping the input space. These are just colored, and you see that they also are not randomly distributed, which is known because colors are associated to photometric redshifts, etc. Anyway, so why this is relevant? So, because what we are after is to quantify how a training set is matched to the target data, to the target multi-wavelength data. And we did it by using exactly the same maps, where instead of features or some other quantities, you can just count how many objects you have per cell, randomized to some quantity, and here they're randomized to the sky area because different surveys have different sky areas, and what you're interested in is some projected density of the objects. And you see that if you just take the full catalog, then there is some distribution, and if you take the training set, the numbers are in many cells much lower. You can just divide one by the other, and then you get something like a completeness map, although note that it can go above 1 because this is not really exactly completeness. There is both randomization in how you build this map, but also there are some other reasons that you can have something above 1. Basically, the training data can have some overrepresentation in some because there is large-scale structure in the universe, for instance. There are some, maybe groups of galaxies which have the same colors and the same redshift. But anyway, such a map already tells you quantitatively in which of the cells you have too few galaxies to really well represent your target data set, which is there. So ideally, you would like to have close to 1 everywhere. And once you have such a map, then you can say, okay, now I go to a given cell, I pick up this cell, and then from the input data, I just have a catalog of galaxies which don't have good representation in the spectroscopic data. What I can do with that? So I can either, for my scientific analysis, just remove all the galaxies from these worst cells. This is something done for some reasons. If you want to be sure that your photometric redshifts, for instance, are well trained. But you can also be more ambitious and try to fill them up with new data. And this new data come from two sources. One is the public data which are coming up all the time. And just 2 days ago, there was a huge data release from an American instrument, DESI. But we also applied for time on telescopes to try to fill up these cells. It was a very successful endeavor. In September, we had a summer student, Joanna Kociesz from Kraków, supervised by Priyanka and me, and with the help also of an observational specialist from Warsaw Observatory. We applied to ESO with 2 proposals. We got 1 accepted, and Priyanka and Joanna are actually going to Chile, and I'm jealous a lot because they only had 2 places, so I decided the student and the postdoc should go rather than the PI. I also don't know how to do observations anyway, so. And just yesterday, there was another deadline for ESO proposal, so we resubmitted a previous proposal which was not accepted, and we hope for the best. And we chose really targets from the least complete cells. Yeah, so here it's discretized, but actually there are, of course, some particular numbers, and these were really very close to 0, and you have a list of galaxies that you can just choose and ask for observations. So that's my final slide. Thanks.
Thank you, Maciej. Any questions?
Quick technical one. So if you are saying that you are applying for the telescope, it means that you can, as you said, say that I wish this telescope is watching this point or this part of the sky. How it's?
Yes. So in ESO, basically, you have there is a list of telescopes which are available in a given call. Okay. Poland is part of ESO, so we can apply. We don't have to pay for that at all. And then you choose which telescope you want to use for your science, okay? You have to write a proposal saying that this telescope is the most appropriate, and then you choose in particular whether you want to do photometry, so images, or spectroscopy, spectra, yeah? And here we applied for spectra. And then you have to provide a list of targets which will be visible in this given time of the year, because these are calls for half a year basis. And you build a scientific proposal that you say why this is important, why you should be given time in this very competitive process, which is very competitive. I mean, there are tens of, I think even more than tens of submissions every time. And there is a committee that evaluates the proposals, whether this given science and these objects are worth being given time on the telescope. And there are some telescopes where you have to go, well, have to or want to go there, and you do really observe that. That will be happening with Priyanka and Joanna. But there are some others which are, there is local resident astronomers and you don't go there. For large telescopes, you stay home and you wait for your data to come at some point. And so that's how it works.
Okay, and the last question.
I wanted to go back to sort of the basic question on this. So if you have this machine learning classification of the kids' data, what are the basics of what you actually get from this? Is it a matter that you can have an idea about the spectroscopy of these galaxies that you only have photometry for? Or is it a matter of getting better signal to ratio in the whole sort of data set or something?
Well, there are a few things here. So first of all, you can use these maps just to learn more about your data. For instance, already from that you can compare in a given cell how different quantities are associated, which is not always obvious. Yeah. For instance, so stellar mass, as we call it, M star, is a physical measure of what is the total mass of luminous matter in a galaxy. While photometric redshift is, when you try to estimate its distance, it's not really related, but you see that there are some correlations which are due to data selections. So this is one thing you can learn. Second is that if you now, this is just for your full data set that you do it, but you also, if you want to learn how some data that you think are good for training some supervised model to do something, for instance, photometric redshifts, how appropriate is that? You have to try to quantify this in some way, and this is what we do here. I'm not sure if this answers your question, but okay.
Okay, let's thank Maciej again. So I would like to thank all of you for coming, asking questions, preparing nice presentations. Before we go for pizza, there will be one more by me, which summarizes all our activities at the Institute last year. Okay, so this is the photo taken in 2022, which we use for all occasions. We should take another one, so we should meet again here maybe. And well, most of people are still here, so okay. So this is our institute in numbers. We have 95 articles last year. 9 of them were for 200 points, 51 for 140 points. So a bit lower than the previous year, but at the same time, the number of researchers employed at our institute dropped a lot by 10. So I would say that we are better in terms of the percentages as compared to the previous year. We still have 9 PhD students, but this number gets down because well, people defend their thesis, leave our institute, and we don't get any new grants. Okay, these are the projects that we received in 2024. We received 4 national projects from NCN. There was NCN Maestro to Professor Janiuk, NCN Prodium Bis to Professor Korbicz, NCN Sonata to Dr. Haber, and also NCN Opus to our director, Professor Pawłowski. We received 4 international grants, financed or co-financed by the European Union. And the main one was the ERA Chair project, already mentioned by Krzysiek today. So there were many people behind preparing the application. It was a great success. There is also this EU QEC for QEA, which will be led by Michał Oszmaniec. I helped him in preparing the proposal. There are also 2 other grants by Michał, which were brought from NASC. And the total number of projects is 30, so we increased even the number of projects. We have really a lot of projects, I would say, as compared to the number of employees. Okay, these are the, so we, as I said, we had 9 papers for 200 points, and these are the papers in the best or high impact journals, however you call them. It's very nice that we are able to publish in the journals like Nature. So there were 2 Nature papers by Professor Janiuk, and one was also co-authored by Professor Czerny. There was one in Nature Materials by Professor Matuszewski, and the paper that Michał today presented in Physical Review X. So the most important facts that happened in our institute last year. So the first one is creation of a new project department. We hired Dr. Anna Reiter-Smilianic and then Dominika Koszade-Karwat. Anna will take care, or is already taking care of the European projects. Dominika is taking care of the NCN project, so probably you have met them already. They are very good. I'm very happy that this project department was created. And it has now 4 people, because we also have Kasia Sobczak, who is taking care of the financial business of the projects, and also we hired one person, Krzysztof Szczegielski, who is helping Ania in managing our ERHR project. We had an opening for a tenure track position that was settled this year, so we soon will hire Patrick, who won the competition. Then we had a renovation in our headquarters at Aleja Lotników, which was successfully completed in September last year. So Magda was the main driving force behind the whole project. She was coordinating everything, she organized everything, and we are now happy. I had 2 visitors at Aleja Lotników, and they were really happy about how the institute looks now. They said that the place looks very nice. So I'm happy about this, we are happy about that. We received the EU Central Project, ERA Chair. I'm still amazed by the fact that we were able to get it without any previous experience in preparing this type of proposals. We are participating in some European projects, but to write from the scratch a full application, yes, so I'm amazed. So this will bring us a new research group, and also Professor Marzena Szymańska already joined our institute. She's already hired at our institute, and she will come for vacations this year. So if you want to collaborate with Marzena, please approach her. Then Professor Janiuk received a prestigious NCN Maestro grant. Okay, these are the prizes and awards from the last year. So Professor Szyszkowski received Quantum Award for his achievements in entanglement theory. This award is being awarded by organizers of this conference. Then Karol Szyszkowski received an ERC Advanced grant. It's not our grant, it doesn't go to our institute, but nevertheless, I'm very happy to announce that our researcher was able to receive such a grant. And also Professor Agnieszka Janiuk received a computational time on the Lumi machine, and she already mentioned that today. Okay, these were the conferences and workshops that we managed to organize last year. There were 5 of them, like the main ones. I would say some of them were already mentioned. So Greek meeting on Cartan geometries was mentioned by Katja during the talk. That there was the clues workshop organized by Maciej and Wojtek and their collaborators. It was also mentioned. Then there was a conference organized by Professor Janiuk, Professor Czerny and their collaborators, also mentioned today. And then there was this Mazowian Symposium on Quantum Optical and Atomic Physics, mascot, not mentioned today, I think. Krzysiek probably forgot, but we organized it together with the University of Warsaw and the Institute of Physics of Polish Academy of Sciences. And the main person from our institute was Krzysiek, actually. It was a very nice workshop held actually in this place. And I with Jarek and Ovidusz, my former PhD student, organized Quantum Information Days, also here. We managed to gather 70 attendants, which was, well, the conference was very nice. Okay, these are the PhD theses defended in last year. So 2 of them were me, Rafael Freitas dos Santos, and Ovidusz Makuta. So Rafael defended his thesis at the beginning of the year, Ovidusz in October, then Jakub Kopyciński with Professor Pawłowski, and Suhani Gupta with Professors Helwing and Bilicki. So I'm very happy that we are having PhD students that successfully defend their thesis at our institute. Okay, we also applied for patents. So 2 of them by Michał and Michał Oszmaniec and his collaborators, and they are related to the TeamNet project that was on quantum computing that we ended, I think, last year. And am I right that they are related to the? Okay. And then there was also this patent application with a method of tuning chordophones, which is related to Paweł Norowski's recent activity on how to construct pianos with different number of tones in a scale. Okay, challenges. I think that the main challenge for the next year is to find a new space. So we are going to grow this year because we received ERA chair project. We are going to hire at least 10 people, so we'll have to put them somewhere. So this is the one thing. The other thing is that we are going to join the ERC Synergy Gravitas of Professor Hrustiel, and he will also come with people. And we will also hire Patrick, who won our competition. He will also bring people. So this is, in my opinion, the main challenge that we have to face this year. We have to find space for all of them. Okay, thank you. That was all. And Krzysiek wants to say something.
I just want to say about this space. So we made the projection, and it seems that we'll have to have next year around 90 people. And actually there is Polytechnica shown, just this bottom left corner. And we have an agreement for rental the space only until the end of this year. So previously we were receiving always contracts for like 3 or 2 years. And this time they extended this only by 1 year with actually the signal that we have to find something else. So that's why I are lobbying for this additional space.
Okay, thank you, Krzysiek. So that's all. Thank you for coming.